Hello, everyone. Today I'm going to be doing an introduction on machine learning for game developers. My motivation for doing this is that all the machine learning information out there is kind of tailored towards people working in Python. When us game developers, we work in C++, and they're just completely different worlds. But here at EA, we have a lot of machine learning experts and a lot of game development experts, and it'd be kind of nice to bridge that gap a little bit. And also make the machine learning black box be a little bit less of a black box. So first up, here's the overview. We're going to first talk about multi-layer perceptrons, which is the classical type of neural network. We're then going to talk about gradient descent, which is how you train neural networks. And then we're going to talk about 3 methods for calculating gradients. After that, we're going to put it all together. I'm going to show a recipe for how to train a neural network to recognize handwritten numerical digits, and then how to actually use that in practice. The training application is just standalone C++ without external libraries, and the demo that actually uses it is, again, just C++ in DX12, just very plain. Should be real easy to see what's going on. Okay, so first up, let's talk about multi-layer perceptrons, aka like vanilla neural networks or classical neural networks. So some terminology to start out is, if you look on the right, we have a neural network there, and it has 2 layers, a layer being just a group of neurons. There's the input layer on the left and the output layer on the right. And each layer has connections between all neurons in both layers. And so that means that it's fully connected. And if you see the W's, those are the weights. And the weight is just the strength of a connection between a node. And so like when you have an input and you're trying to calculate an output, you multiply the inputs that go into one of the neurons by the weights, and you sum those all up. Then you add the bias, which is the B, the bias for that neuron, to give you your final value. So it's like a scalar value for that neuron as its output. Before actually using that output value, you put it through an activation function, which is like just any nonlinear thing, like taking the sign of the value, and then that goes on to the next thing. So in perceptrons, they take a vector floats in, which that's the input neuron values, and it gives you an integer out. And so they're binary classifiers. And what I mean by that is either the outputs are going to be 0s and 1s, or you're going to do something like, say, the largest output is the winner, and that'll be the index, the integer that we're giving as output. When we're training these networks, we give them both an input and an expected output for that input, and that makes it supervised learning. This is in contrast to unsupervised learning, which would be something like you give it a bunch of data and you tell it to try to classify it into like 3 different groups, and you don't care how those groups are organized. That would be unsupervised learning. When you go through the entire set of training data once, it's called an epoch during the training. And there's often several epochs during training. And if you update the weights and biases several times during an epoch, it's called mini batching. And how much you update the weights during training is called the learning rate. We'll go into the details of some of these as we go on, but I just wanted to give you some basic terminology. Okay, so a little more information about how you actually evaluate or execute a neural network, which is also called inference, is that if you're trying to calculate the output for a specific output neuron, you find all the things that connect to that neuron, and you multiply the weights by the value of the neuron going into that. So, for output 1, it's going to be input 1, 2, and 3 times their respective weights that go into that output. After that, you're going to add the bias term for the output 1 neuron, and then you're going to use the nonlinear activation function to get the final value, which for perceptrons, the activation function is basically just if the value is greater than 0, set the result to 1, I'll set it to 0. And I'm going to call this the sine function from now on, even though it's not what you might think of if thinking of a sine function. So yeah, that's how you calculate a neuron's output, which is, it's not too complicated. But as simple as that is, we could actually simplify it a bit more. If we take the input vector and add a 1 to the end, and then we take the weights vector for each neuron and add a bias to it, we can actually just get the output by doing a dot product and then having the activation function be done on that. So you can see that in the first chunk of code on the left. And if you wanted to get both output values here, you would do 2 dot products, which is just a matrix multiply. So in the second chunk of code there on the left at the bottom, you can see where we do that. We do a matrix multiply to get the output, and then we apply the activation function to each part of the output. So as you can see, it's pretty straightforward to evaluate neurons in a neural network or layers in a neural network. And also because it's matrix multiplies, it's also very GPU friendly. Okay, so time for the first exercise. There's going to be 4 exercises in this presentation. And basically the idea is that you can pause the video, go do them, check out the solutions, and then come on back. And so in this exercise, we're taking the perceptrons on the right, which there's 2 types. The top one has 2 inputs and 1 output, and the bottom one has 1 input and 1 output. And you're going to take these and make the logic gates with them, the traditional logic gates of OR, and not, and then also exclusive OR. And I have the link here on the slide that says where more instructions are and the solution is. So go ahead, pause the video and give it a try and come on back. Okay, cool. Welcome back. If you gave that a try. If not, we're going to go through the answers for this exercise. So here we go. Okay, so there's multiple ways to solve these things. So if yours looks different but still works, that's totally fine. So for OR, what I did was I set both of the weights to 1 and the bias to 0. And what that ends up being is just that we're adding input 1 to input 2, and those things can either be 0 or 1. And then we're putting them through the sine function. And so if you look at the truth table on the right, you can see that it gives us the desired results. Okay, so next up is AND, which again, the weights are 1 in my solution, but this time I changed the bias from being 0 to being -1. And so now it adds the input and output and subtracts 1. And so this way it requires both inputs being 1 for it to be above 0 and thus give a 1 as output. Okay, next up is NOT. And for this, I did a -1 for weights and a bias of 1. And so you can see that if you plug in a 0 into the input, you get a 1 in the output. And if you plug a 1 into the input, you get a 0 as output. And so next up, we're going to check out XOR. And if I had to guess, I bet you had some problems with that if you tried it. That's because it was a trick question. Hopefully you didn't spend too long trying to figure that out and pulling out your hair. But so there's an interesting lesson here, and that is that a perceptron cannot actually do exclusive OR without adding a hidden layer. It's a limitation of what it can do. And so by adding the hidden layer, you're able to do exclusive OR. And here's the weights that I used, which probably look like nonsense, but there's some intuition here. And that's that the hidden 1 neuron only gives a 1 as output if only input 1 is on and input 2 is off. And then hidden 2 is the reverse of that. Hidden 2 will only give a 1 as output if input 1 is off and input 2 is on. And then what we're doing is we are ORing hidden 1 and hidden 2 together to give us our final result. And so looking at the truth table, you can see that it gives us what we want. So cool. Hopefully you had fun with that. It's kind of a different way of thinking. Okay, so next up, let's talk about gradient descent. So gradient descent is how we train neural networks usually. And so let's talk about training real quick. So when we evaluate a neural network where we give it some input and then we get the output, when you're doing training, what you want to do is put the output through a cost function. And the cost function will give you a cost or a score that says how well the network did, or rather, the value it gives you is how wrong the output was for that input. And so what our goal is that we want to adjust the weights and the biases within the neural network to give the lowest cost function for the input we gave it. So yeah, that's the goal. And there's two ways that I'm going to mention about getting there. So kind of two ways of training it is, one, you can just generate a whole bunch of neural networks randomly, like randomize the weights and the biases. And you might generate 100 or 1,000 or 10,000 or more of these and just keep whichever one does the best. This can work well for small networks, but when you have larger networks that have, thousands of weights and biases or more, this becomes a lot less effective. And so what people usually do instead is they will start with a randomized network and then they will try to improve it. And so that's what we're going to be talking about. And so to improve the network, you are optimizing the cost function. And what that means is that you're essentially trying to find the lowest point on the function. And so if we look at the left, where we have a simple parabola, it's like y equals f of x. You can think of x as being the weight or the bias of a neuron, and we're trying to find the value that gives us the lowest point on the curve. And so an easy way to do this for simple functions is you just find the derivative of the function, set it equal to 0, and then wherever those points are, you can look at them to see if they are the minimum that you're looking for, like iterate through them. But if we look at the middle picture, this is more like what a neural network is actually dealing with, because each parameter to the function you're trying to optimize is one of the weights and biases. And there's often, like I said, like thousands, 10,000s, lots more. And so what that means is the dimensionality of the neural network is often, extremely high, in the thousands, because it's the number of parameters. So what can you really do? Well, the cost function ultimately returns a single value that's the score. And so like using intuition from the real world, you can just kind of drop a ball randomly on this shape and let it roll downhill. And wherever you end up is going to be a minimum. It might not be the global minimum. It might be the local minimum, but you're going to find a minimum. And so like, as you can see on the right, if you start at the wrong spot, you might end up in a local minimum instead of the global one that you're looking for. But there's some hope for this, and that is that as the number of dimensions increase, that this problem of local minima actually decreases, because when you get caught in a shallow valley for one dimension, is that it's likely not a valley for all the other dimensions involved. So you can kind of roll to the side and escape the local minima to try to find the global one. And there's also a technique called ATOM, which upgrades gradient descent a bit, and it adds the concept of momentum of this ball rolling, and also adaptive step sizes. And that can help you reach the global minimum and help you reach it faster. Okay, so the physical intuition of rolling downhill makes a lot of sense, but how do you do that mathematically? The answer is the gradient. And the gradient is just a vector of derivatives of the function. So if your function takes 2 parameters, your gradient will be a vector of size 2, where each entry is the derivative of each parameter. The nice thing about the gradient is that it points the steepest direction uphill. And so since we're trying to find the minimum, we just go the opposite direction, which will be the steepest direction downhill. And unfortunately, the path to get to the global minimum is often not going to be a straight line. And so you want to follow the gradient, but because it's not going to be a straight line, you want to take small steps and reevaluate it. And so this is kind of like what the learning rate is all about, is the size of the step that you're going down the gradient. And so cool, yeah. Now that you know how derivatives can help get you to the minimum of a function, it's probably important to explain that this is why differentiable programming is important. Because if you make a program, or like a part of a program that's differentiable, that means that you can optimize it using gradient descent to find the best values of your parameters towards whatever your goal is. And if you've heard of differentiable rendering, this is the same idea there as well. You might have an ambient occlusion rendering algorithm that has a lot of parameters for how it works, where it shoots the rays and things like that. And you might have a ground truth that you took from, taking 100,000 rays per pixel, something like that. And if you have a differentiable renderer, you can tune your parameters to, find the global minimum of the lowest error of your render versus the ground truth. And so that's kind of why differentiable renderers are important. Okay, so moving on, let's next talk about 3 different methods for calculating gradients. So we'll start off with finite differences, which this is like the easy mode way to get derivatives and gradients. So what it is like, if you think about what a derivative is it just tells you for a function y equals f of x, it tells you how much y changes when you take a step on the x-axis. And so if we want to know what that value is, like, we can just do that. So how finite differences works is you know the y value of where you are at for your x value. And so you take a step on x, reevaluate the function, and then however much you changed in y divided by your step size tells you your derivative, or it tells you the slope of the line at that point. And here, epsilon is like the step size you're taking, and we have the formula for it at the top formula. You can imagine that if you had a wiggly function, if you took too large of a step size, that it would give you the wrong answer, right? So the smaller the epsilon value, the more accurate the derivative you're going to get. Where at the limit, as e approaches 0, you're going to get the exact derivative. However, since we're using computers and floating point, you also don't want to go too small, because then you'll hit floating point problems. And so it can be kind of like a delicate act trying to find the right epsilon for your usage case. And so that's forward differences, but there's actually something else called central differences. And that is, instead of only taking a step forward on x, you also take one backwards. And so now you have 2 different y values that surround where you are on the x-axis, and you divide by twice the step distance. This is more expensive, but it's also more accurate. And if you just look at the formulas, it looks like we're just evaluating f twice in both cases. So why would it be more expensive? But the reason is that a lot of times, and especially in neural networks, you already have the value of f of x. And so when you have to do f of x plus a step, it's just one extra evaluation, where with central differences, you're going to have to do the 2. Okay, cool. Time for the second exercise. This is again at the GitLab repo. There's instructions and a solutions document to try. So go ahead, pause the video, give it a try. Okay, and welcome back. We're not going to go over the rest of the exercises, because it's just kind of like, they're meant to be like exploration to give you some hands-on experience. And yeah, like the ways you choose to explore are going to be different than other people. Okay, moving on from finite differences is we get to dual numbers, which is the second way of calculating gradients. And this is also known as forward mode automatic differentiation. So first we'll talk about dual numbers, and then we'll talk about how to use them to get gradients. So dual numbers are very similar to complex or imaginary numbers, where those guys, they have an I squared equals -1. But with dual numbers, we have an epsilon squared equals 0. And importantly, epsilon itself is not zero. So one way to look at it is that epsilon is just the smallest number greater than zero, so that when you square it, it does become zero. And this probably sounds a lot like how we were talking about the epsilon in finite differences, where you get the correct value as epsilon approaches zero. It's kind of the same idea here. But epsilon can also be represented by a matrix, as you can see on the slide. If you multiply that matrix by itself, it gives you the zero matrix. So much like complex numbers, dual numbers come in the form where it's like a plus b times epsilon, where a is the real part and b is the dual part. And so using dual numbers to get a derivative is in the form a plus b epsilon. You set a to your x value and b to the derivative of x, which is just 1. So you have your value plus epsilon. And then when you plug that into your equation, you can do math as normal. And just the only thing you have to watch out for is that if you have e squared or any other higher power of e, you set that term, you set it equal to 0. And when you're done doing all your simple algebra, the result will be an a plus b epsilon. And a will be your function's value at x, and b will be the derivative. The cool thing here is that this is not a numerical method. This gives you the exact derivative. And so that makes it better than finite differences in that way. And you can extend this to give you the derivative of multiple variables at a time, and also higher order derivatives, like if you want the second derivative or anything like that. So let's work through an example real quick to see how this works. So let's take the function 3x plus 2, which is just a line. And let's say that we want to calculate it at f of 4, and we want to also get the derivative at f of 4. So what we do first is we have to make dual numbers out of x, 3, and 2, our variable as well as our constants. So for x, the value is 4 and the derivative is 1, so that just becomes 4 plus 1 epsilon. For 3 and 2, they're constants, so we set the real part to their value, and we set the dual number to 0, the dual part to 0, because the derivative of constants is 0. So then if we plug that into the equation and just do simple algebra, making sure that any e squared term is 0, we get our result, which is 14 plus 3 epsilon. Now, the cool thing is the 14, which is the real part, is our value of the function at f of 4. And the 3 is our derivative at f of 4. So yeah, it worked. If you want to try this out yourself, that's kind of a fun little thing to do, just like make an equation, try to plug dual numbers in and see if you get the right answer out. But a cool thing about dual numbers just working like regular numbers is that you can make a class, kind of like how complex numbers have a class or a struct, and just do operator overloading for all the math things. And then what that allows you to do is if you have a function that you've written to take in some parameters and return a floating point value, you can change that function from using floats to using a templated type. And then you just pass in your dual number, x value, or whatever your parameters may be. And it'll run the function as normal. But when you're done, you'll have both the values you wanted as well as the derivatives, which is pretty cool. It's makes it a nice way to use dual numbers. Okay, so time for the third exercise. This one, again, is there in the repo. There's some instructions and the solution. It's a code exercise like last time. And in this one, you're just going to be implementing addition, subtraction, and multiplication in dual numbers for it to be able to do gradient descent and optimize a function. So go ahead, give it a try, and then come on back. And welcome back. And again, that was mostly for exploration, and there's like the solutions there, so we won't go through the details here. Okay, last but not least, the third way to calculate gradients is through backpropagation. And this is kind of like the pro mode gradients. This is what people actually use for the most part. And what it comes down to is using the chain rule. And if it's been a while since you've taken calculus, the chain rule is just the fancy way of saying that you can do cross cancellation on derivatives just like you can as if they were fractions. And so yeah, let's see how to do it. So if we think about the cost function of the neural network on the right, it's kind of a couple of nestings of functions. So to calculate the cost, we put the activation of the output neuron through the cost function. And to get the activation of the output function or the output neuron, is we put the raw output of the neuron through the activation function. And then to calculate the raw output of the neuron is we are going to multiply the inputs by their weights, add those together, and add the bias. So, right, like that's how you evaluate this neural network. So next up, we can kind of get the derivative of each of these nested steps. And so first, we can say that if we change the activation, we can calculate how much that affects the cost. And so that's our first derivative, which is delta cost divided by delta activation. And the derivative of that is just the cost function's derivative at the activation value, right? And so we can do the same for finding out how much the activation changes when the raw output changes. And then we can also do that for the weights and biases. And so like for weight 1, we get the derivative of how the raw output of the neuron changes as weight 1 changes. And then once we have those derivatives, we can actually just multiply them together left to right. And as you can see in the purple, doing some cross cancellation of those derivatives, we're left with delta cost of delta weight 1, which in English means if we change weight 1 by 1.0, if we add 1.0 to weight 1, how much will that add to cost? And that's what this fraction, this derivative tells you. And on the right of the purple, you can see it's pretty simple to calculate. So yeah, backpropagation, it's pretty fast, pretty straightforward, and it can be intuitive, but if it's been a while since you've used the chain rule, it takes some time to get back into it. One thing to watch out for with backpropagation, though, is that there can be multiple paths to affecting the cost function. So like right here, if we want to get the delta cost of delta bias 1, so more plainly, how much the cost is affected by us changing bias 1, is that we actually have two paths. Because if we increase bias 1, that's going to affect the neuron hidden 2A as well as the neuron hidden 2B. And so to find out how much we affect the cost, we have to add both those paths together. Just kind of like a little detail that's easy not to realize when you go and try to write your own neural network evaluation or training. And okay, time for the last exercise. So much like the last two exercises, the goal here is to provide the derivatives for it to be able to do gradient descent on a function. This time, though, the functions are nested, so you have to use the chain rule. So go ahead, give it a try, and come on back whenever you're ready. And welcome back again. So let's compare the three methods we talked about for calculating gradients real quick. So finite differences is pretty cool. You don't actually have to know anything about the internals of the function you're getting derivatives of. Like it could be a call into a DLL or even a call over the network where you can't even look at the assembly. It can just be a total black box and you can get derivatives of the parameters, which is cool. A problem, though, is that it's only an approximation. And since you have to do one or two evaluations of f for each variable that you want a derivative of, it can get really slow, especially for neural networks that have thousands of parameters at minimum. Dual numbers are a little bit better in that they give you exact derivatives. Unfortunately, the function you're dealing with can't be a black box. In practice, that usually isn't too big of a deal, though, because you need to be able to modify that function to make it take a templated type so that you can give it dual numbers. But a downside to this is that dual numbers are also very slow and they take a lot of memory because let's say you're evaluating a network that has 10,000 parameters to optimize, like weights and biases. That means that every single variable, literal, temporary, local, all those things are going to have, that many floats inside of it, tens of thousands at minimum. And so that's a lot of memory. And when you're doing addition, subtraction, multiplication, it's going to have to go through all of those floats and do operations on them. So not super great from that perspective. And then lastly is backpropagation, which is very fast, and we'll see that in a second. But it also gives you exact derivatives, just like dual numbers. The downside to backpropagation is that you really need deep integration and deep knowledge of the function that you're trying to get the gradient of, so that you can do the chain rule at each step. But choosing the method you're using to calculate your gradients is not like an all or nothing thing. You might choose to be doing backpropagation like overall, but if there's parts of whatever it is you're optimizing that it's difficult or impossible to get like symbolic gradients from, you can use one of the other methods, such as dual numbers or finite differences, to get a derivative to include in your backpropagation. And yeah, even some like some of the big Python packages will actually do this. They'll mix these up since they're situationally best. Okay, so that was it for like the prerequisite info to actually be able to do some training and execution of neural networks for a real usage case. So let's get into it. So talking about how we're going to set up the network and train it first, we're going to train the network on something called the MNIST dataset, which is a bunch of hand-drawn digits. And I've included some here on this slide, showing a bunch of zeros. These images are each 28 by 28. And so what that means is if we want to plug these into the neural network, that's 784 pixels. So we will need 784 input neurons. Besides the input layer, we're going to have a hidden layer with 30 neurons. And then we are going to have an output layer with 10 neurons. When we're evaluating the network, whichever output neuron has the largest output value is going to be considered the winner. And that index is going to be the value that the network has recognized. So, if output 0 has the largest value, then we will say that the network recognized it as a 0. If output 5 was the largest value, then we'll say that the network recognized a 5. So adding up all the layers, this is 824 neurons. And if you add up all the connections and biases, that makes almost 24,000 parameters that we're trying to optimize, which is quite a bit. But as far as neural networks go, this is actually a pretty small network, if you can believe it. Okay, so that was the topology and kind of like the overall of what we were going to do for a network. For training, the MNIST data set has two subsets of data. There's 60,000 digits that are used for training the network, and then there's 10,000 that are used for testing the network after training. And so what we're doing here is we're training with the 60,000, and then we're evaluating the quality of the result using those 10,000. The reason why we do this is because neural networks and other optimization techniques, they will sometimes overfit the training data. And so what that means is that they're very good at the training data, but they're not any good at anything else. And so if you take your training data and reserve some for testing, what you're doing is you're allowing yourself to test the network on data that it's never seen before. And that'll tell you if it's overfit or not. So for our activation function, instead of using the sign function we've been talking about so far, we're going to use a sigmoid function, which is essentially a differentiable step function. If you know tone mapping, it probably looks pretty similar. And that's essentially what we're doing, is we are taking all possible floats and mapping them down to 0 to 1 for a step type situation. When we're doing training, we're going to do 30 epochs. So we're going to go through those 60,000 numbers 30 times. We're going to shuffle the order of the numbers each epoch. And we're going to have a mini batch size of 10, which means when we're running through those 60,000 training items, every 10 items, we're going to get the average gradient of for the cost function, and then we're going to adjust our weights and biases. We're going to use a training learning rate of 3.0, which that means we're going to multiply our gradient by 3 before subtracting it from the weights and biases. And then for our the cost function for our entire network is we're just going to sum up the cost function of each of the 10 output neurons. And the cost function for a single output neuron is going to be 1/2 of the desired output minus the actual output squared. Or another way to think of this is it's 1/2 of error squared. And we added the 1/2 because when you take the derivative, it cancels out with the square, the power of 2. And so that means that your derivative is actually just going to be actual output minus desired output, which is nice and simple. Okay, so I'm going to show you this thing in action, but first, a couple more things. I train this thing with each of the 3 gradient methods, and I want to talk about those. We did end up with 95% accuracy on the 10,000 training data images, which, to put that in perspective, that means 1 out of every 20 it got wrong, which is a pretty large error rate, but this is kind of like a toy level neural network. So pretty decent results for like just a toy. But yeah, there's like larger networks and convolutional neural networks and different activation functions and such can get you better results than this. So training with finite differences, we basically had to evaluate the function 24,000 times to get each gradient for each input, which is kind of a lot. So I spread this around 18 cores using OMP and did some other optimizations, and it still took 6 hours. Yeah. And using central differences, which takes double the number of function evaluations, that one took 11.5 hours. So quite a long time to train this pretty small neural network. Using dual numbers instead to get gradients, as soon as I tried it with the naive implementation of dual numbers, I busted the stack because every variable, temporary, local, constant, all that stuff, it had 24,000 floats inside of it. And so I just like ran out of stack space immediately. So I made a sparse dual number class and made a sparse pooled stack allocator and just hit it as hard as I could with the profiler, and still could only get it down to 28.5 hours, which is over a day, which is kind of insane. And yeah, backpropagation, it only took 90 seconds. I didn't really have to do anything special for profiling either. So I think this just goes to show how macro optimization can be such a much bigger win than micro, as we all know from game dev. But it would also be interesting to try these things on the GPU and see if their characteristics changed at all. So next up, I'll show the demo, but I want to show quickly how I'm actually running the neural network in the demo. Here's the render graph where the blue boxes are resources like textures and buffers, and the orange boxes are compute shaders. I've circled the 2 compute shaders that are the ones that actually do the neural network evaluation. It's just those 2. And plugged into them is this buffer that I circled that's 93 kilobytes of floats. These are the weights and the biases that were trained by the training application and just loaded into memory onto the GPU and fed to these compute shaders. The rest of the compute shaders and textures and buffers are basically there for UI. So yeah, here's the demo. Before I actually launch it, I want to show you here in the profiling window. It's only taking 283 microseconds total, so less than a third of a millisecond to recognize the digit. This is on a 3090, but yeah, super fast. And so let me actually launch up the demo and show it to you in real time. Okay, great. So here's the demo. You can just draw using the left mouse and see it recognize a 0, a 1, a 2. And when I clear it, it's important to note, when it's getting nothing, it thinks that it has a 5. This is pretty interesting, but if you think about it, we train the network only on digits. We never give it anything invalid, and we give it no way to express that something was invalid. And so it has to make a guess, so 5 is as good as any, I guess. The other things being shown here, when I draw a number, this first box here shows the 784 input neurons arranged as pixels. This next column of boxes, this is the hidden layer, and then the last column of boxes is the output layer. And yeah, again, when you profile it, you can see here that the hidden layer, it's actually taking less time. It's it looks like 150 microseconds total, which is just super fast, super fast. So yeah, that's the demo. And you can fire up the demo. It's just C++ and DX12, no external libraries. So you should be able to just, open it up and compile it. I did it in Visual Studio 2022. So if you're using 2019, I might complain about that, but just tell it can convert. So in closing, hopefully you see that this stuff isn't so scary. Like backpropagation is probably the scariest part, but it's not that bad. And if you need to, you can always go with a simpler option, and just pay the cost of longer training times. But really, the important thing I wanted to show here, besides demystifying all this stuff, is that while training neural networks and similar can be really slow, actually using them at runtime can be extremely fast because it's just some matrix multiplies, which those are pretty fast, especially on the GPU. So I feel like I want you to know that you shouldn't be afraid of running these things at runtime, even though training takes a long time. And if you're wondering kind of like where to go next in your machine learning knowledge, one way to go is you can actually modify the training application that's there in the repo on GitLab, and you can try adding momentum to the learning, or go read up on how Atom works and try to implement that. You can also try a different activation function like ReLU or CeLU, especially for the hidden layer. And then you can also try using a convolutional neural network instead of the fully connected perceptron type of network that we did. Convolutional neural networks tend to do better with images, which is exactly what the MNIST dataset is. So it should work better there. You can also try training on different stuff. Like there's another training set like MNIST, but it's called CFAR10, and it's just some color images that you can train a network on, like they all have labels. And if you experiment and get better results or worse results, it'd be great to hear from you how that worked out. And then lastly, there's also something called Onyx Runtime that we have an EA wrapper for. And this is basically a thing that helps you run inference, or rather execute your neural networks at runtime more easily and more efficiently. So we do have an EA wrapper for it, and it's in use in games like FIFA, but it isn't Frostbite specific. So if you're not using Frostbite and you're interested in that, that's a thing you can use, which is pretty cool. And then lastly, I wanted to say, we have a lot of game development experts here at EA, and we have a lot of machine learning experts too, but there isn't a lot of overlap between the two because one is bare metal C++, and GPU optimization for game dev, and the other is like working in the world of Python and advanced mathematics and like research papers. There's not a lot of overlap there, but I really feel like if we can help bridge the gap between our two worlds from both sides, that we can really do some amazing things. And so I think like a good place to do that is at the machine learning SIG. So hopefully we can get some conversations going there and try to build a bridge across and do some really cool next gen stuff. And that is all. Thank you so much for listening, you guys. Hit me up if you have any questions.